All right. So we're talking about polynomials and factoring them. And let's start with this concept of why that's important. If I take a linear equation, what does it mean when I take y and set it equal to 0? It finds the value of x that makes y equal to 0. And what we discover is that means that it's not where y is 1 or 2 or 3 or -1 or -2. It's where y is equal to 0, which turns out to be the x-intercepts. And of course, we have other tricks for finding the y-intercepts. And in this case, that would allow us to, that was an awful graph because I wasn't watching it. It allows us to graph the expression. Why is it important to graph this expression? Well, if I look at something like x plus 5 equals 8, how many solutions are there to this? 1. I can subtract 5 and I get that x is equal to 3. This is an equation that has a single solution. How many solutions are there to this? Infinite. I cannot possibly list out all the solutions. Therefore, it's a function. In other words, I look at the relationship between them, and the best way to describe that function is often with a graph. What if I give you that idea, in other words, another function, but this time I give it to you in a format that produces a quadratic? Is it still a function? Right? We could multiply this out. We've learned how to multiply things like this. This is now a quadratic in standard form or in factored form. With either one of these, we should be able to graph this. And what shape would this turn into if we graphed it? A parabola. And we would express it as, okay, what would happen if the y is equal to 0? Well, I'd use the zero product property to say that the only way two things multiply together to make 0 is if one of them is 0. So either x plus 2 is equal to 0 or x minus 3 is equal to 0. In this case, x would equal -2. In this case, x would equal +3. And if I then plotted those, I would then be able to say, okay, well, I know the y-intercept is down here at -6. And so I could then plot this as a parabola. And what this is all like, this is algebra 1. This is the spring of algebra 1. Then you guys did advanced algebra, where we talked a little bit more about that and introduced the idea of cubic equations. And if I had a cubic, it would still be the same thing. If I set this equal to 0, I could find the value of x that would turn it into 0. And there's reasons that that's valuable, in addition to it being able to graph it. There's other things that situationally are important. So in the test you guys just took, you had to think about what the end behavior of this looked like, right? As x approaches infinity, f of x approaches what? For this function. I usually end up drawing it over here to think about kind of general, that's a cubic function. So as the x value gets bigger and bigger and bigger, the y value gets bigger positive or bigger negative? Positive. And as x approaches -infinity, f of x approaches what? -infinity. Okay, good. So this is the kind of stuff that we're looking for on the last test. And with that vision, I can then recognize my zeros of 2, -3, and -4. And I could plot this sort of. This is not an accurate representation, but it gives me an idea. And then we got into a little bit more detail and said, okay, what if we have multiplicity, right? What if we have x plus 2 and another x plus 2 and x minus 5? You'd say, okay, well, let's put a little negative out front. If I did this, now I know that because it's got a negative there, it's going to be going the other direction. And so now as x approaches infinity, f of x approaches what? -infinity. And then as x approaches -infinity, f of x approaches +infinity. And when I graph this thing, I'd know that my zeros are +5. And at -2, what happens? it bounces. Instead of crossing through the x-axis, because it's got multiplicity here of 2, we know that it's going to come bounce that point instead of go through it. It tries to go through it, but then it has to turn around and go back through it again for the second one, basically. And it bounces and then comes back like this. All right, this is where we've been to last week. And then we started looking at what happens if we have something like more complicated, like f of x equals 2x cubed plus 11x squared plus 28x plus 24. Okay, this is cubic, right? So we know this should end up being 3 things, 3 factors. Do we know what the first terms are going to be? All of them are x's? If I have 3 x's here, those would all multiply to make a single x third. That's not what I want. I want 2x to the third. So one of these has to be a 2. 5. I understand that. That part makes sense. 3, sort of. I'm a little unclear on that. 1, what are you talking about? How do we know that? Okay. So when I FOIL this thing out, I'm going to go over it a little bit better because I think there's some people who are confused. When I FOIL this out and I multiply these 2 things together, this factor and this factor together will form a binomial, excuse me, a quadratic trinomial. And if I then multiplied it by 2x plus something else, when I distribute my lead terms, that would give me my 2x cubed. And the only way I can get that is by having an x in each of these, and one of them have a 2. Is it possible that one of these is actually like 4, and one of these is a 1/2? Well, sort of. But if that's the case, this 1/2 could be offset by pulling a 2 out of here and then distributing back through. Let me make that a little bit clearer. Let's say that I had something like 2x squared plus 4x plus 2. This might work out pretty easily. So I could treat this as 2x and x, and then I could recognize this is a 1 and this is a 2. And this would be a valid factorization of this, agreed? Could I also then pull a 2 out of here? And would that also be a valid factorization of it? Could I also do this? And is it the same thing? If I distribute this 4 through, I end up with a 2x. If I distribute this 4 through, I end up with a 2. All of these represent the exact same structure. Which one is best for us? I would look at this one. That's the easiest for me to see. And so when we look at this environment, we're trying to look at what the lead terms would be. Forget about the fractions and pulling out too many like we did here where we get fractional lead coefficients. We don't want that. We want simple coefficients that are integers. So I know it's going to be x, x, and 2x. But I don't know about these last terms. What your homework was last night was to help figure out what those terms have to be. So last night it talked about the idea of if I've got a cubic function like this, I can consider this p and this q. And the possible rational, which is also real, roots are what? How do we come up with what the possible things are that you put into your synthetic substitution or division? P over Q. So what are all the factors of negative 24? Well, we could have 1 and 24. We could have 2 and 12. We have 3 and 8, 4 and 6. 5 doesn't work. Is it worth going into 6 and 4 again? And now 8 and 3 again? No, because I've already done those. So I'm not going to worry about those. But I also have to worry about the positives and negatives of these. So it could be plus or minus 1, plus or minus 24, plus or minus 2, plus or minus, right? And does this list now have all the possible rational roots in this mix? Those are all the factors of 24. Is that all the possible rational roots? We have to do it for 2 also. We need the Q. Why does that matter? Because if we go back to this other idea, what if I ended up with a root that was something like 2x plus 3? And then I said, okay, so when is this root equal to 0? Because there's a lead coefficient of 2, I could end up with fractions where I end up dividing by 2. And so this has to be a possible root if there's a lead coefficient of 2. So when I look at this thing, since there's a lead coefficient of 2, I don't just list all these possible rational roots. I have to also take all of them divided by 2, so plus or minus 1/2. Do I need to worry about 24 over 2? No, because I've got 12. Do I need to worry about 2 over 2? No, because I've got 1. Do I need to worry about 12 over 2? No. Do I need to worry about 3 over 2? Yes. 8 over 2? Nope, that's covered. 4 over 2? Nope, that's covered. 6 over 2? Nope, that's covered. This is now a comprehensive list of all the possible rational, which means real, roots of this polynomial function. Who's with me on that? 5, I could create that list of possible rational roots easily. 3, sort of makes sense. I'd probably miss a couple of those. I might forget the plus or minuses or the 3/2 or something. 1, this is confusing to me. Okay, great. In your notes for today, this is our first piece. So let's just finish that off because now I've covered that for you. Those of you that just came in, come grab one of these. Okay, recall that a polynomial function of degree n can have at most n real roots. And real roots can be rational or irrational. What does that mean? What's rational mean? It does mean reasonable, but not in the terms of math. It can be represented by a fraction, right? We look at the word ratio in here. So it can be represented as a over b, where these are both integers. So it could be 1/2. Could it be 6? Yes, because 6 over 1. What's an example of an irrational thing? Like root 3. You cannot express that as a fraction of 2 integers. Rational zeros are those that can be written in the form of a fraction of 2 integers. P over Q. The rational zero theorem can be used to determine all possible rational zeros of a polynomial function. If we've got some f of x that it's a sub n of x to the n plus a sub n minus 1 of x to the n minus 1 plus dot, 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 all the way down to a to the first, or a sub 1 of x to the first plus a sub 0. if all of these coefficients are integers, then every rational zero of the function has the following form. P over Q, where it's factors of the constant term, A sub 0, over the factors of lead coefficient, A sub n, and then plus or minus. So let's take a look at number 2 here. Can I have individuals, please, raise your hand and take turns telling me one possible root? One. You don't get to say another one. You've said one. Someone else. 3. Good. 6. Someone else. We've got 24 people in here. That should be enough. 9. Good.
2.
2. Good. 18. Good. Is that it? Good. Plus or minus all of these. So 1 times 18 makes 18, 2 times 9 makes 18, 3 times 6 makes 18. Now that's all of them. Now, it's also possible that our roots are not rational. That means they come out with like square roots of 3 in answers. You had a problem like this in your work 2 nights ago, I believe. How would you factor this one? When you look at this, what do you recognize? Would you do synthetic division on this, or would you use a different technique? All right. You would diamond problem this. You would recognize that effectively you could replace x squared with z, and you could then call this z squared minus 9z plus 18. That's a quadratic. And so you could diamond that and say, all right, well, I know that it adds or it multiplies to make a positive 18, and it adds to make a negative 9. What are the 2 numbers that multiply to make 18, yet at the same time add to make a negative 9? Negative 6, negative 3. So now I could express this as z squared. Instead of a negative 9z, I'm going to split it up strategically. Minus 6z minus 3z plus 18. I'll factor by grouping, pulling out a z here. And then I want this to end up with something in front of this same factored term. So I'm going to have to pull out a negative 3. And that means I can factor this entire thing as z minus 3 and z minus 6. Well, that z is actually representing x squared. So this is really x squared minus 3 and x squared minus 6. And I had someone come to me last week and say, I want these to be the difference of squares, but they're not. Right? Why is this not a difference of squares? Because the 3 is not a perfect square. Or is it? If this had been a 4, x squared minus 4, then you would call this x plus 2x minus 2, right? If this was x squared minus 9, you call it x plus 3x minus 3. I can still treat this as a difference of squares. It's x minus what and x minus what, or x plus what? Root 3. Right? It is the square root of 3. And what's the other pair? X minus root 6 and x plus root 6. We can still use the structure to solve these things. And if I looked at the actual zeros of this, my solutions would be x equals plus or minus root 3, comma, plus or minus root 6. Maybe we'll put those in set notation to demonstrate. Any questions on that? Yes. This part. So this is called factoring by grouping. And although if this is a leading coefficient of 1, you can just jump to the end and say it's z minus 6 and z minus 3. Is that what you would do? Okay, it won't work here for f of x over here in number 2, because the lead coefficient is not 4. It's not a 1, excuse me. So this technique works all the time. It's a little bit extra work in this case, but let's do this one. What's our diamond? What's on top? Good. We're going to multiply this 4 times this 8 and get 4 times 8 is 32 on top, positive. And what goes on the bottom? Minus 33. And what will be my left and right parts of that? Let's see. We're going to want them to multiply to make that. But we want them to be positive, so they have to be the same sign, while at the same time adding to make a negative 33. So it's going to be negative 32 and negative 1. That means I can express this thing as 4x to the 4th minus 32x squared minus 1x squared plus 8. Notice this time I didn't replace it with the z. If you're comfortable just leaving it in the same 4th and squared terms, this can be a little bit faster. If you want to use the z, you can go for that. This is where the factoring by grouping really comes into play here. What's common to these two terms? Good, 4x squared. And when I pull that out, what I'm left with is x squared minus 8. And I want this one to have that same interior piece. I want this to be x squared minus 8. So what do I pull out in front here? Good, negative 1. And now it's really factoring by grouping again. I'm looking to see what's common in this factor as well as this factor. What's common in both of these terms? X squared minus 8. And if I pull that out of this one, what's left? And if I pull that out of this one, what's left? So this is my factored form. But can I go further? And I treat this as a difference of squares. Okay, it's going to be x and x. It's going to be minus and plus. And what's going to go in here? Root 8. I'm going to simplify that because I know that's got a piece in it. 4 and 2, 2 and 2. So this is 2 times 2 times 2. A 2 can come out, a 2 stuck on the inside. So it's x minus 2 root 2, x plus 2 root 2. What about in here? What's my lead term? Good. Square root of 4x squared is 2x. 1 minus 1 plus. And what about the last part? And since we're actually finding the zeros, the values of x that make this function equal to 0, we'd say if this part equals 0, then x would equal 2 root 2. This one gives me the negative 2 root 2. What's the 0 for this one? One half, right? You'd add the 1 to both sides. And then divide by 2, and you get 1/2. And we're going to end up with both positive 1/2 and negative 1/2. Is this still basically P's and Q's? Yes, but you're going to end up with some other weird components, irrational zeros. Please try number 4 yourselves now. We're going to tie in together what we did with P's and Q's, and you're going to have to use synthetic division to find this one, I think. No, actually, this one will factor by grouping. Factor this one by grouping. Pause the video for a second while you do this. So thank you. Yes, I've fixed that. That's plus or minus 2 root 2. Now, even though this was x to the 4th, this was quadratic in nature. We could solve it with our factoring tools like the diamond. When it's a cubic one, we can't do that. In the event that it works out that this is factoring by grouping, that works fine. This is really 3 times x times x times x. This is really 3 times 5 times x times x. What's common to those two? X squared and 3. And so when I pull out the 3x squared, here I'm left with x. Here I'm left with minus 5. And now if this works with factor by grouping, I should be able to find the same thing inside here, x minus 5. What could I pull out to make that work? Negative 4, good. And now again, I look at this and say, okay, there's an x minus 5 in this term, and there's an x minus 5 in this term, so I can pull that out. That's common. And what I'm left with then is 3x squared minus 4. Now this is already a linear term, so I'm done with that. But this one's quadratic. I should be able to take that further. How should I factor that? You could do difference of squares. It's going to be particularly ugly. You might also think about, okay, well, I know that this thing could be 0. So I could say 3x squared minus 4 could equal 0. Add 4, and I get 3x squared is equal to 4 over 3. Excuse me, is equal to 4. And then I divide by 3, and I get x squared is equal to 4 over 3. What's the next step? Almost. When I take the square root of this, what do I get over here? Plus or minus root 4 over 3. Whenever you introduce a square root to solve something, you got to bring out the plus or minus. In this case, this needs to be rationalized a little bit. I'm going to say plus or minus root 4 over root 3 plus or minus 2 over root 3. How do I rationalize that? Root 3, so this becomes plus or minus 2 root 3 over 3. That gives me my 2 roots, which is what I expected for a quadratic. So my zeros here end up being 5, and then plus or minus 2 root 3 over 3. The process is the same, whether the roots are rational or irrational. It just adds on a little piece on the end. Questions about this? Okay. What we're working on this unit is getting more and more complicated with our polynomials. We started with simple ones. As they get more complicated, we might need to bring in some more tools. One of these tools is called Descartes' Rule of Signs. René Descartes was famous for many things. He was a philosopher, but also a great mathematician. And he came up with this rule of signs. He recognized that when we work with polynomials, we can get a little bit more information about the zeros, what we're going to be pulling out as our factors, if we pay attention to the changes or the variation in the signs. Is this a positive number or a negative number? Positive. What about this one? It's a negative number, right? So is there a change in sign between the first and the second? Yes. So there's one change there. This is negative and this is positive. Is there a change of sign there? There is. So there's another change of sign. This is positive. This is positive. Is that a change of sign? This is positive. This is negative. Is that a change of sign? This is negative. This is negative. Is that a change of sign? It's not. Therefore, in this case, there's 3 variations of sign. And what René Descartes was able to figure out is that the number of positive zeros is equal to the number of variations in sign less an even number. So in other words, I could have 3 or 1 positive real zeros. What does real signify? What are we talking about when we're saying real zeros? Not just rational, it could be irrational. No imaginary numbers. We're excluding the imaginary numbers. No i's involved in this. Now, here's what's interesting. He recognized, remember we did symmetry tests? Where we plugged in like negative x for x or negative theta for theta and compared it. If I take this same expression and I plug a negative x in, In other words, I find what happens at f of negative x. What will this first term become? It'll become a negative because I'll put negative x to the fifth power, which makes it negative. What about this next one? Does it change signs? If I put a negative x to the fourth power, the negative goes away, right? It becomes positive. So this is not going to change. Will this one change signs? It will, because an odd multiplication of negatives, negative times negative times negative, will change this sign to a negative. What about this one? Will it change signs? Negative x squared is still positive x, so this will not change signs. What about negative x to the sixth? If I put a negative x in here, I'm using negative x instead of x. What will this part become? Positive 6x. And this is a constant, so it won't be affected by swapping in negative x. So how many changes of sign do I now have? One there and one there. So that tells me that for this function, I'm going to have two, or an even number fewer than that, 2 or 0 negative real roots. When this is a fifth degree function, how many roots altogether do we expect? If I wrote out my parentheses, how many parentheses would I have? 5. And this shows me that of those 5, 3 of them will be positive real roots, which means it's going to be x minus a. And 2 of them will be negative real roots, which means it'll be x plus a. But it's also possible I could reduce it by 2 in both cases. What's that all about? Why are we reducing it by 2 each time? Well, we'll get to that in a second. So let's take a look at just applying Descartes' rule of signs for this. Let's count the number of changes of signs in number 1. This is positive. This is negative. That's 1. This is negative. This is positive. That's 2. So the positive, how many will there be? 2 or, nope, 2 or 0. You're lessening it by even numbers. Now let's take a look at f of negative x. When I plug that into x to the third, will that change my coefficient sign? It will. Negative 2x cubed. What about this second term? Will that change signs? It will not, because negative x squared stays the same, so my sign will stay the same. What about this next one? Will it change signs? Yep, so negative 2x plus 1. So how many sign changes do I see in here? Just 1. Therefore, my negative roots, real roots, are going to be 1. Can I subtract an even number from 1? No. 5. Okay, I understand how to apply Descartes' rule of signs. I don't really see a lot of value in it yet, but I do see how to do it. 3. I'm getting there. Not really sure about it. 1. I have major questions. Okay. Once you guys do number 3 now, while I pause this for a second, let's make sure everybody gets this. Okay, so we went through this and most people are feeling pretty good about this. How many times do I have a sign change in this first one? 0. So in other words, my positive real roots, I'm not going to have any of them. If I do trying negative x, I'm saying 2 times negative x to the fourth plus 21 times negative x to the third plus 27. So that's 2x to the fourth minus 21x cubed plus 27. Now how many sign changes? How many sign changes? 2. Going from the lead coefficient to the negative is 1. From that negative to a positive is 2, or 0. So if I were going to try to do this one using P's and Q's, what decision could I make based on this? Let's do this. What would be the P's and Q's for this one? What are the possible rational roots for this? It'd be 1 and 27, 3 and 9, and then each of those over 2. And then should I do plus or minus? Normally, yes, but I have no positive roots in here. So would I ever test positive 1? No, why would I? It's not going to work. So I would only test the negative numbers. In other words, I just cut out 8 possible things I could check. I just saved myself so much time if I were going to actually find this one. Does that make sense? Any questions on this? All right. Now, why were we subtracting even numbers, subtracting 2 each time? The reason is because the fundamental theorem of algebra that you guys have been applying since you learned about the zero product property says that if you've got a polynomial function with a degree n, where n is greater than or equal to 1, then it has at least 1, 0 in the complex number system. If it's a polynomial with a degree n, and n is greater than or equal to 1, it's a linear or a quadratic or a cubic or a quartic or a quintic, then it has at least 1 0 in the complex number system. We know that, in fact, it has the number of zeros equal to n. And if C is a complex 0 in a polynomial function, then x minus C is a linear factor of it. Okay, so what does that mean? Well, these are just formalizations of what we've been talking about. If I want to factor this, how would you begin? What do you look at and decide to do here? Excellent. This is another diamond problem. You see that this is the fourth, this is the second, there's no third or first, therefore I can treat this as a quadratic. F of x is equal to x squared here, x squared here. My diamond is going to let me say negative 25 times 1. So negative 25 on top, negative 24 on the bottom. That's going to be a negative 25 and a positive 1. Now, I just jumped to that. This is what Mari was asking about earlier, right? We can do this because the lead coefficient is a 1 rather than doing the factoring by grouping. What about this one, x squared minus 25? How does that factor further? Almost. Good. X plus 5, x minus 5. That's a difference of squares, no problem. What about this one? See a little louder? Can we treat this as a difference of squares? No? What if I called it x squared minus negative 1? Is that now a difference of squares? This is a perfect square. This is a minus because it's a difference of, and this is negative 1. So couldn't I say it's x minus square root of negative 1 and x plus square root of negative 1? which is I, right? X plus 5, X minus 5, X minus I, X plus I. Pro tip, if you didn't like this difference of squares over here, we could have also said, I know that x squared plus 1 has to equal 0. That means x squared has to equal -1. I can solve that by square rooting both sides. And when I square root, what do I have to do? Plus or minus. So x equals plus or minus square root of -1. That shows me that it's x is plus or minus I. Now, please remember that we're talking about polynomials here. That means they have to have real coefficients. All of the leading coefficients in any of our polynomials will be real numbers. They won't have i's in them. And if they don't have i's in them, then when I FOIL this mess out, I need my i's to cancel out. That means every single time my i's will show up in conjugate pairs. Remember what that means? Do you remember when we did like rationalizing complex numbers? How would you rationalize this? 3 plus I over 3 plus I, right? Remember that? And the reason we do that is because this bottom one will become 9 minus 3i plus 3i minus I squared. The I terms will cancel out, and we'll get 9 plus 1 is 10. That's the whole point of the conjugate pairs. By doing a difference of squares, the I, the middle term, will disappear. What we're working towards is this idea that if I give you the zeros of a polynomial, let's say that I tell you that the polynomial is a 5th degree and that it's got roots of 2, 3 with a multiplicity of 2, and then 2 minus I. What we're working towards is your ability to say, okay, I can produce that polynomial in factored form. What would my first factored term be? Good. X minus 2. That gives me this one. What would my, someone different, what would my next factor be?
X minus 3.
Good. Someone else new, give me the next one. I think someone said it really softly. Good. Another x minus 3 because it's multiplicity of 2. Now, use that same idea. What would be the factor with this as a term or as a 0? X minus this thing, right? Just like here, we said if this is a 2, I do x minus 2. If this is a 3, I do x minus 3. If our 0 is 2 minus I, wouldn't it be x minus 2 minus I? What we're talking about for these imaginary ones, these complex that have imaginary components, is that the only way this can turn into a polynomial is if this next factor, the last one, is what? Very good. X plus 2 minus I. It has to be a difference of squares so that the middle terms will cancel out. Five. That makes perfect sense. I now understand why we're subtracting 2 when we talk about real roots. 3. I'm sort of getting this conjugate pair thing, but it's not really clear yet. 1. Huh? All right. This is definitely taking us a little bit ahead. For the rest of tonight's homework, you are going to be doing these factorizations, and you're not going to have to come up with the conjugate pairs, but you will discover as you do this that you always end up with a pair of conjugate matching complex numbers. All right, this is your packet for the day. This is what you'll work on. If you haven't already finished 59 and Access Pearson, please do that too. Thank you.